In clinical oncology, a familiar and frustrating pattern repeats itself. A patient receives targeted treatment. The bulk of the tumor mass dies off, but a hidden subpopulation of cells survives. Over time, that tiny fraction overtakes the tissue, establishing what is known as clonal dominance. When a cancer returns stronger and resistant to therapy, it often feels like a biological mystery. It isn't. The inability to predict which cells will survive is a structural flaw in the mathematical models we use to track them. Current models suffer from premature scalarization, compressing 3D cellular data into a flat, one-dimensional line. As ghost-like icons of age, signaling, and metabolism drift away, we lose the joint state history. Without this temporal data, the model fractures, blinding us to therapy-resistant lineages. By simplifying the math for computational convenience, we are mathematically blinding ourselves to the exact cellular states that allow cancer to survive. Solving this requires a shift in how we handle population data. We have to stop compressing the numbers and adopt a framework that preserves high-dimensional geometry across every scale of the tumor. This is achieved through the age-structured renewal operator. It is a mathematical framework designed to track exact cell lineages without losing historical data to simplification. This detailed branching tree represents level 1 of the framework, unfolded coordinates. At this microscopic level, we track the granular age and unbroken lineage of single cells, ensuring no temporal data is lost. As we zoom out, we reach level 2. Those individual branches bundle together into folded clonal population counts. This correlates the microscopic lineages to the mesoscopic data seen in laboratory colony assays. Pulling back fully reveals level 3, macroscopic density transport. This describes the physical mass of the tumor as it expands through the tissue, treated as a continuous flow. This 3-level architecture allows us to map abstract functional analysis directly to the 3 ways biologists actually observe cancer in a clinical setting. Historically, it was difficult to translate data between counting individual colonies and measuring the continuous mass of a tumor without violating the rules of mass conservation. To bridge that gap, we use Jacobian weighting, represented here by the equation 1 over lambda. It acts as a permanent mathematical marker that connects counting-based and density-based representations. This factor ensures that as the tumor expands, the macroscopic data remains perfectly synchronized with the microscopic branching. Because the math is weighted to conserve mass, no data points are dropped during the translation. Because this framework tracks the specific signaling states and age of every cell, it can identify what we call the deterministic spine. While most lineages hit treatment-induced resets like apoptosis and fade to gray, this specific path follows a multiplicity-weighted renewal identity, a biological countdown clock that keeps its growth bound above a critical threshold. We finally have the arithmetic precision to track the specific lineage that avoids treatment-induced death to become the next dominant clone. The irregular signaling and growth noise of malignancy, seen here in these rapidly dividing cells, historically made it nearly impossible to prove that any population model was unique or stable. We resolve this using a measure-theoretic architecture. By proving that active cancer populations occupy the full measure of the tissue, we gain the mathematical stability required to track them firmly despite the biological noise. This diagram shows the order convention bug in older models. They used prefix-based logic, starting with an initial mutation on the left and trying to guess the future by branching forward into dozens of uncertain, fragmented endpoints. The suffix rigidity theorem reverses the flow. It tracks backward. By starting from a known terminal resistance state on the right, it traces a definitive line backward to determine its exact origin and the sequence of differentiation that created it. Mathematically reversing how we look at time allows us to correctly classify which clonal populations are stable and pose the highest risk of relapse. We are moving away from scalar models that discard temporal correlations. By preserving the joint state history of every lineage, we can identify resistant clones that were previously hidden in compressed data. Utilizing the spectral geometry of these operators provides a certificate for the joint age state of the tumor. This allows for numerical auditing of growth rates at a level of arithmetic precision that traditional counting methods cannot reach. We no longer have to rely on approximate growth rates. We finally have the mathematical resolution to see the growth bounds of a surviving population before they manifest as a relapse.